Alrighty, guys. Good morning. Thank you for your patience while I fiddled with a lecture 2 lectures ago. It dawned on me the other day, and it dawned on me when I was putting some questions together to see if we had enough questions for the test. I mentioned the Hawaiian Islands and mentioned that they were slightly different. There isn't actually a slide about it, and I'm not sure why. Again, this is one of those where I swear I used to have a slide about it, and I don't know what would have happened to it over the years. But so I was Googling real quick to try and find something, and lo and behold, I stumbled across the actual national park site for the Hawaiian Islands. So a hotspot is usually close to the surface pool of magma. I don't think they really understand why they are. And I just saw that sort of reiterated on the park site. It's not horribly big. It's just a couple hundred miles, which sounds big, but again, we're talking about the whole scope of the Earth. So, so it's been feeding. As it leaks through the crust, it's, because you kind of picture it again as a big a zit or something very close to the pimple, close to the surface, hasn't broken through yet. But when it does come to the surface, well, that pimple is a volcano. And what's really neat about this is that it anecdotally ended up providing some great evidence for plate tectonics back when they were still struggling to prove that it was a thing. Nowadays, we've got GPS systems nailed into mountains and so on and so forth. We can see not just that the plates are moving, but how fast and in what direction and everything. But back before that, we needed, more evidence. Any evidence is great. And it turns out that indeed the Pacific Plate is moving northwest. I'm stealing from the next slide. We see that this island chain goes off to the northwest. Also, of the, let's see here. 8 islands in the chain. I'll come back to this slide, but in the 8 islands in the chain, they grow older as you go off towards the northwest. What a quinky-dink. So the one that's farthest out is the oldest, and then subsequently younger, all the way down to the active island. And I don't know about you guys, but I never really learned my Hawaiian island names very well. I could rattle off a couple, but so the one that the big island there now is Hawaii. So the island of Hawaii, and there's the chain, the Hawaiian island chain. So the island of Hawaii is the youngest of them. All right. And also, again, as they pull away from this hotspot, they become inactive. Wow. More neat evidence. So it really is a thing, and like I said, it's kind of neat. But that's why, again, we acknowledge that they're in the middle of the Pacific Ocean, nowhere near that plate boundary, and I mentioned the word hotspot, but we didn't really go any further than that. So... and then now just a couple factoids. There's actually 5. The island of Hawaii is made up of 5 volcanoes. But you hear the most about Mauna Loa and Kilauea. Okay, because they are, not AIF, they are the most active ones. All right, Mauna Loa looks to take up the majority of the island there. And as we said, there's 8 islands in the chain. And they're going off into a northwesterly direction. And there's a new one forming. It'll be thousands of years, they say, before it reaches the surface, but there is Loihi that is just moving onto the plate as Hawaii slowly slides off of it. So a couple more slides for next semester's folks, and like I said, just in case you happen to see a question on the next test about hotspots, you'll be slightly more informed. So today I want to use the balance of our time to finish up talking about, bless you, the three types of rocks. Okay, we started with the rock cycle, and then we went on to igneous rocks. We touched on volcanoes because, well, they're made of igneous rock. Then we went on to sedimentary rock, acknowledged that we're skipping weathering and erosion and a whole bunch of stuff that we're going to come back to. And then, as I said, today we want to talk about metamorphism and or metamorphic rocks. In the lab, metamorphic rocks really just gets, I don't want to say a couple of minutes, but nothing compared to sedimentary, okay? We talk about them, we look at them. They're funny. They're the simplest and they're the hardest rocks. They're the simplest in that there's really just two things to look at, the heat and the pressure. And you guys heard that back when we did the rock cycle. But they're harder, more complicated, because if you actually stop and look into the heat and the pressure, it's really nuanced. Okay, there's so many subtleties and so on and so forth that affect in the way these rocks turn out. And it's a spectrum. It's not just you're this or you're that. There's a whole lot of in betweens. So again, a 14-week class in and of itself can be metamorphism. We're going to give it half an hour. Okay? So, and half an hour in lab, so we'll give it a total of an hour. But, so not a whole lot about metamorphism in GL 101 typically. So, without further ado, let's get rolling. So, you may have seen a rock, stripy rock, like this. People love to decorate with it in landscaping and so on and so forth. You will come to know and love this rock, hopefully. You guys usually end up calling it the zebra stripe rock. I just want to caution you, the first of many times, that the stripy rock, which is heretofore known as gneiss with a G, comes in other colors, okay? But you see the black and white all over and over and over. I've actually got a purpley yellow one. I don't know what that came from, but it is really cool, and it happens to be a pebble sort of rounded thing, so it almost looks like an Easter egg. It's really cool. I haven't seen it in a while. Hopefully it didn't walk off. But yeah. So, you guys are going to memorize it as the zebra stripe rock, but now why is, when I go here, it's nowhere near the edge of the slide, but when I project, sorry guys at home, that's, as you can see when I go into projection mode there, it's cutting off the first couple letters.
How to project it was formatted in terms of zoom in.
Yeah, zoom isn't changing it. That's what I was thinking. It's almost a perspective thing, but I've never had perspective issues before. Well, I've had a lot of personal perspective issues, but never projecting perspective issues. I don't think widescreen is an option here.
Sure.
You guys see it in there? I don't.
Nope, I don't got it.
Well, hopefully it won't affect us too much. The letter that's missing is an M, yeah. And there's that pesky rock hammer in the image again. All right, so how do we define metamorphism? Well, metamorphism is defined as mineralogical and or textural changes that occur in a rock due to exposure to extreme pressures and or temperatures. All right, we got that and or in there twicely because exposure to temperature does one thing, exposure to pressure does another thing, and you're not always exposed to both. So that's why we've got the mineralogical and or textural changes and the pressure or temperature. As you'll see, you can't, if you get one of them, sometimes you can't help but get the other one, but sometimes you can get just the, let me rephrase that. You can get just temperature by itself, but if you're going to have pressure, you're going to have the temperature too. So you can have temperature without high pressure, but you can't have high pressure without high temperature, if that makes sense. So, as we mentioned, changes in temperature and changes in pressure, okay? And these are fairly big changes that we need to make, all right? When we talk about pressure, yeah, a little bit from burial, but it's really not enough to do anything. We're kind of talking about, like a car crash on continental levels in order to get this stuff. And if you've actually driven by, a road cut and seen some of this bended rock, you got to imagine that does take a lot to do that. And not just that, when you see it all bent up like that, imagine if you tried to do that with and it was all cold and hard, it would have just shattered. Okay? So that's where the heating element comes into it. We want this to be, as malleable as we can. It is a very slow process, don't get me wrong. And, most anything can be bent eventually, but the heat definitely helps make some of those cool bends. And I hope, it's been a while since I've seen this PowerPoint, so hopefully we'll have some cool pictures in here, and you'll see what I'm talking about. So where does that heat come from? That heat comes from, the center of the Earth, right? The mantle is quite warm, and that's because of its proximity to the core. You've heard the geothermal gradient before, all right? They've estimated that the core is around 9,000 degrees Fahrenheit, and it goes down from there. There are, as always, anomalies, okay? But yeah. And the rest of the Earth essentially sort of acts as an insulator, which keeps the core nice and toasty while absorbing some of the heat itself. Funny that we just took a couple minutes at the beginning today to talk about one of the exceptions, hotspots. We mentioned igneous intrusions at the end of the igneous rocks conversation a couple lectures ago. This one shows the Yellowstone caldera. The picture isn't super big. I apologize if it's hard to read from the back. So this reiterates, even though we just talked about the Hawaiian Islands as an example of a hotspot, we've got one under the Yellowstone Park, okay, as well, and that is, we mentioned, I think, at the time, what heats up all that groundwater. Igneous intrusions are also an exception. We talked about those, how they sort of snake their way through cracks in the rock and work their way up towards the surface. You've got magma where it isn't supposed to be, pressure because of that, and follows the path of least resistance, wiggles up through there. They've managed to combine both of those into this Yellowstone graphic. So not only do we have this hot spot, but it's there's drawing that it is intruding in, sort of making a fluton. Remember, that's that pool of magma up there. So yeah, fitting it all in. So before we leave this slide, I just want to make it clear. Generally speaking, when we're talking about metamorphism, you need to bring the rock to the hot. Okay, we need to get a rock into the side of the Earth. Every so often you can bring the hot to the rock, but that's the exception. Okay, that's the exception to the rule. More often than not, you've got to get, via that rock cycle, you've got to get the rock into the Earth. Pressure. So, like I said, burial is responsible for some low-grade stuff. Nothing great. Lithostatic. Lith, again, means rock. We've mentioned that or come across that word a couple times. Static, unlike, you guys aren't old enough to have heard static on a radio station. I don't know if anyone still has a dial on their radio. But There used to be something called static, and you could get it on the TV too. And listening to that, you wouldn't think that the word static means constant, because it's all over. It's a whole bunch of different noises. All right. But static, stasis, they're related. All right. Static means constant. So this is constant rock pressure. That's what lithostatic means. And that's basically just burial weight. All the rock on top of you, you got to admit that's got to be heavy, right? Is pressing down on you. And if you want some sort of evidence as that is the case, there's time after time again where we've gone in over the years. Nowadays they know how to look for this, I guess, for lack of a better word. But we've gone in, we've pulled a whole bunch of rock out of the way to throw up a Walmart or some such thing, and the rocks underneath just almost sigh with relief and they bow, okay, because the pressure was removed above them. So it is a thing, and the rocks do respond to the absence of and the presence of that lithostatic. But again, when you think metamorphic rock, you're usually not thinking about these guys. On the other hand, tectonic activity, plate tectonics, okay, that's the big guy. Now, please don't worry about this lithostatic versus differential. Please. Just pointing out, since we're in the conversation, that with that you've got movement. You've got movement in directions and so on and so forth. And it's different. Not to say differential, but it is different. And in the lab, we actually talk about this a little bit more when we are looking at rocks that are affected by this. I try to point out this a little more. So if you're feeling unfulfilled at the moment, it will come in lab. All right, so I like the crushed marshmallow thing here. I don't know, I must camp with the scouts too much because I'm just picturing a s'more there. But, so that's lithostatic, okay? I'm not really sure how we're getting the horizontal forces in this second picture. If his foot were going forwards or backwards, I can see how we get a horizontal parallel force there. We get the squishing, obviously. But generally, and again, when we talk about this in lab, I will try to make it more obvious. Again, picture continent smashing into a continent. You've got a direction involved, not just this up and down pressure, okay? There's no indication that his foot is moving forwards or backwards, to me at any rate, just down. And we want that directional movement because we want to move those mineral grains around in the rock. So maybe these are both just examples of lithostatic. I'm looking now that I see the title up there, but I see the arrows coming in from the left and the right, and that's what made me think that they're trying to show. Yeah, my bad. There's the differential. See, it has the direction. Maybe I'll white out a couple of those arrows from the sides on that other one so I don't get confused next semester. Picture this as a deck of playing cards or something, okay? And you push against it in a direction and you'll get that movement. And we can actually see the grains orienting in a particular direction. When it's in the lab, completely removed from its source, you can't tell anything. But if it were still in the ground where it was originally, harvested from, you could say, oh, well, the force came from the northwestern direction, and you see how it da-da-da-da. But in the lab, all you can see is that the stuff lines up. It has a direction of flow, as it were.
Does it always have to be opposite? Like with tectonics, it is, you got your rock in the middle, and then bottom pressure, top pressure. Can it be top pressure this way and bottom pressure that way?
Well, like the bottom picture is showing there, you could have two ways. I mean, yeah, it really.
Can it be like multi-directional?
It really depends on the interaction. When we talk about plate interactions a little later in the semester, maybe keep that in mind. I really like the car crash illusion there, and where you're just getting rumpling, okay, and it keeps it kind of simple, and that's where we've got again just two plates coming together, and there's rumpling, crumpling in between them, and even though you're essentially moving, dare I say it, at 90-degree angles, that hardly ever happens, but you're going to get rumples that go in a bunch of different directions because of inherent weaknesses and so on and so forth, and the rocks that you can't even account for. So you get all kinds of. This is a simplification for sure. But if you're talking about some sort of side-by-side motion or any angles involved, yeah, it can get as crazy as it needs to. But like I said, keep that question in your mind when we talk about the different ways that plates can interact, and maybe in that context, you'll find your answer. But right now, we just want to keep it simple. Whipping out the delta. You guys all remember what delta means, right? Nah, some of you.
Triangle.
Yeah, the triangle. Does not mean triangle. So, if you had chemistry ever, delta means change. All right, it's just a short way of writing. It's a shorthand of writing change. So, when you see delta capital T, capital T is temperature. Excuse me. Lowercase t is usually time, right? Anywho, so delta T is change in temperature. Delta P is change in pressure. So what we're saying here is that mineralogical changes come from changes in temperature. Textural changes come from changes in pressure. Now, as I may or may not have babbled a little while ago to you guys, that might even be in this next slide, you can get the first one, you can get temperature changes without pressure. But if you're seeing a rock that's been exposed to pressure changes, it undoubtedly went through some temperature changes as well. So you can do the first one without the second, but you can't do the second without the first. And again, I think this is really why I stopped talking about this in lecture. It's so much more obvious when you've got the rocks in front of you. So you're going to see a couple examples of each of these. You're going to see what we're going to come to call foliated and non-foliated rocks. Foliated rocks are the ones affected by temperature and pressure. And I'm sure this will be a slide, so don't worry. And then the non-foliated rocks are only affected by temperature. So some of the non-foliateds you're going to see are things like quartzite and limestone. Okay, I'm sorry, quartzite and marble. Quartzite comes from sandstone, and marble comes from, of course, limestone. And another really popular one is slate. Slate comes from shale or a mudstone. And what we see there is that for the first time, these guys are actually, I don't want to say real rocks. I don't want to belittle sedimentary rocks. I love sedimentary rocks. But with what you guys, this is a rock, good solid hunka sort of thing. When they undergo these exposure to heat, those little grains of quartz in your sandstone or those little grains of calcite in your limestone, they grow bigger and they merge together and they make a coherent sort of thing for the first time. It's not just dirt glued together anymore. So with that increase of grain size comes this melding, okay? Now, on the extreme end, and we don't really acknowledge this too much, we don't acknowledge it in all in lab, but your book, I'm sure, will talk about it. You can also get some remixing of stuff. You get some emerging of things. Serpentine, I think, is the one that comes in the back of my mind. And I haven't talked about that in 20 years. I did a short stint in Baltimore and there was all kinds of serpentine all over the place. So I talked about it then, and I learned about it then, but we don't come across it here too much, and like I said, we don't talk about metamorphism that much. But you take a rock, and because there are a couple of things in there already, again, sedimentary rocks being what they are, a hodgepodge of all kinds of things. When you get these seriously high heats, you can make new stuff. Neat stuff. Mainly we focus on the increased grain size in the merging. So, again, you have this inherent pore space in a sandstone because the irregular size of the grains. And to be fair, the way I word it makes it sound weird. Even if they were perfect spheres, you'd still have pore space. Okay. Again, just picture pool balls in a rack, or a pile of BBs or something. You've always got that space because they're rounded. But when you put them back in this metamorphic oven, those crystals get to grow. Of course, they're going to grow into those empty spaces, giving you a more durable rock and a less porous rock. But we haven't really gotten to the groundwater section yet, so we won't worry about that yet. Textural changes. So I mentioned foliated and unfoliated a couple minutes ago. We call these textural changes foliation. Okay? It's a movement. It's a reorientation of the grains that make up the rock. And again, this comes in a variety of, I don't want to get ahead of my slides here. This comes in a variety of degrees. Again, it is a spectrum. All right. The orientation is, let's just stay on this slide. The orientation is in the direction of the differential stress, the stressor. This opening rock is a great example of what a foliated rock looks like. This is the extreme end of foliation. We're going to teach you in lab, ideally, how to recognize some of the precursors to this. Hence this conversation. I'm sure the folks that are metamorphic geologists, petrologists, study rocks, talk about grading with the non-foliateds. Again, remember, this can be not just a doctorate, a degree to spend your life on, but at very least a 14-week course if you were a geology major. We don't get into it. What we do acknowledge it for, in this case, is with the foliated rocks, because it's really easy to see, relatively speaking. So, slaty, schisty, gneissic textures. You're going to see slate, schist, and gneiss. I'd like to think the names came before the adjectives, but maybe not. So we refer to it as having slaty. I've never heard anyone say slaty. Schisty we do use, mainly because it makes a lot of people giggle. Gneissic sometimes. And what this shows is our low-grade to high-grade metamorphism. All right? And again, I do have a picture coming up. So we're going to talk about it a little bit. I refer to this as a straight-line metamorphism, okay? And even though in this example I'm only going to be providing heat, I think you'll get my metaphor, all right? So what I always talk about is, imagine if you put a baked potato in a microwave and has some sort of time-lapse camera on it, all right? And you watched its progression from a potato to a baked potato to a charred piece of ash at the very end, okay? We're doing the same thing here as we move from low-grade metamorphism up through high-grade metamorphism. We start with a piece of shale or just mudstone. We typically say shale in lab. and we move on to a piece of slate, and then we move on to a schist, and then we move on to a gneiss, and then again, I teach you that after gneiss, it remelts. Remember in the rock cycle, they had that word partial remelting. I told you ignore the partial. All right, we're just going to remelt and become magma again. Forgive me. But it helps bring the rock cycle back home to you guys. Because right now we're down at that 6 o'clock position, moving up to 9. You may not have realized that, but we've slowly been circling through there. So once you get past gneiss, if you keep it in that metamorphic oven too long, it's going to just remelt. So when they're trying to describe a rock before they've decided what to call it, they're going to say, well, it looks pretty schisty, and so on and so forth, or it appears sort of slaty. That's where those adjectives come in. I only even bring it up because our schists vary in their schistiness. So we will talk about that in lab. And blue schist, I don't know nothing about blue schist. But it must be when they just squeeze the hell out of a piece of slate and they don't even bother going through the phases. It comes like it's right out of their cycle there. But at any rate, so I do like this top image here because what it shows us, first of all, is an irregular, just random orientation of grains, right? You've got just crystals all over the place. And then as we start to apply pressure, they're going to organize in one direction. They're going to start to squish down. And then as we approach that differential stressor, they call it shearing in this case, just sliding, then you're going to start to see what we acknowledge as true foliation. You'll hear me in lab, I say, slate is barely foliated. They put it there just out of obligatory, reasons, because you need it to make the schist. But in all honesty, it's not until we start to see that differential stress where, at least in Geology 101, we acknowledge, that hey, this is experiencing some foliation. Okay. Just like I strive to stop saying coarse-grained and fine-grained, I strive to stop saying parent rock. You guys are in college now. We can use the word protolith. What?
Did you say that it's the pressure that causes the slate to become schist, and then the schist becomes...
Increased temperature and pressure. But yes, the pressure is responsible for the foliation. Yes, definitely. But you're always increasing both. But to get think about it. To get the grains to actually move around, we got to put that pressure on them. So yeah, most directly it is the pressure, I would say. So protolith. Again, lith, rock, proto, early, first, prototype, protozoa, first life. You've seen the word proto. So protolith is the right proper word. Okay. I gave you a couple examples already. We told you limestone turns into what? Limestone turns into what? Marble. All right. Sandstone turns into, this one's a little harder. Quartzite. Yep. So on and so forth. All right. Bituminous coal turns into anthracite coal. So the sandstone, the limestone, the bituminous coal, those are the parent rocks or the protoliths. That's what we started with. That's what we're metamorphosing. You'll allow me to conjugate as such. And apparently spell check didn't have a problem with it because it's right there. Metamorphosing.
Can you say what you just said again? Limestone turns to what?
That I can repeat, yes. Marble.
And then what's the
Sandstone to quartzite. You'll get it all in lab, for sure. No worries. That's like the sole purpose of lab.
and will this be on the test though?
On lecture test, not if it's not on the slides.
What was
Probably
the
not.
third one, just so I know now?
I might have mentioned bituminous to anthracite,
Oh, by
Yes.
because there's also shale to slate, but I don't think I mentioned that one. I mean, there's a whole bunch, but. And yeah, I think I've said limestone to marble enough times that that's probably testable. Sure, why not? Not all of you guys will have the Metamorphic Rock Lab before we test on this, unfortunately. So, but yeah, it's always good to know. Like we gave you in sedimentary rocks some examples of what we're talking about. In igneous, we gave you some examples. So yeah, it's a great idea to have a couple examples of what we're talking about here. It gets a little trickier, isn't the right word, because it's not tricky, but it gets a little trickier with the foliated rocks, because what I have you guys acknowledge is the rock before it in the progression. You could argue that the protolith for any of these is on the next slide here. For any of the slate phyllite, the schist, the nice thing, okay? The protolith for any of those, you could argue, is shale. But what I ask you guys to do is use the rock right before it. You'll see that list again in a moment. Just use the rock right before it as its protolith, under the assumption that you can't get one without the other. In lab, you'll learn that that's not always true. But out of respect for the process and for the fact that you guys need to remember these names for the rock test, what am I talking about? Well, I'm going to say for schist, the protolith is slate. Okay? For gneiss, the protolith is schist. So the rock right before it. Yes, they all arguably came from a hunk of mudstone, but truth be told, you could make schist and gneiss out of just about anything. It's a really bad geologic pun. You can turn anything into schist. So, and there's also you could have a schisty gneiss, but you can't have a nice schist. But at any rate, so, but yeah, it is a one-way kind of thing. And again, they love to play with the gradations here. But yeah, please remember the rock before it. Again, that's really something that's more lab oriented than here. But we needed something to, make this an actual conversation, so we're talking about it all in here. So there you go. Like I said, I haven't done this lecture in a while. So there are a handful that are worth knowing. And if you didn't get these down a moment ago, feel free to ask what any of them are. Just in case you don't have lab by the time we have the lecture test, which I really think I'm going to go for next Tuesday. I won't throw it to you on Thursday, but we'll do it next Tuesday. Which means only half of you will have lab. Oh no, wait. You're doing Metamorphics tomorrow. Yay, everyone will have lab by then. Good.
So the test will be Thursday.
Tuesday.
It will be.
I think that's what I said. Yes. That's it. Let's finish lecture. Slate comes from shale. You can put mudstone in parentheses if you'd like. Bituminous coal goes to anthracite coal, yeah. Bituminous, I think.
I think so.
Sandstone to quartzite, limestone to marble. And I don't know how we get so many wicked cool marbles out of plain old boring limestone. All I can say is impurities, because the handful of limestones we've looked at, the handful of limestones we've driven by, as you go about the planet, they pale in comparison to many marbles, right? Do keep in mind though all the statues for thousands of years that were carved out of that beautiful, just solid white marble. So there is, argument for number 7, right? Turning into just white marble. But we love marble not because of that. We love marble for all the cool swirls. So, and yeah, impurities is my answer to that. When you think about it, marble comes from different areas of the world. So, and there's some areas are actually known for the marble that comes from there. Again, it's not an area, something I know a whole lot about, but I would think that it's the local limestone and the impurities therein, the associated minerals, as they say. So, but neat stuff. Everybody loves marble, and then you guys go and you get a unmarbled marble in your Geology 101 class. All right. I think I remember to extract this question from the last test because we talked about igneous intrusions, but we didn't talk about what they can do to a rock that they intrude into. Or if we did, I did it very briefly, but I think I remember removing a question about fake zones. So, as I'm sure you could imagine, the magmatic intrusions are very hot. They wouldn't be flowing if they weren't. And they have some effect on the rock that they're flowing into. And we just got done talking about low grade versus high grade. This is some seriously low grade stuff typically. For one thing, even though this is squeezing into an old crack, that is not the kind of pressure that we're talking about. All right. Sure, it might be uncomfortable for the rocks around it, but not as far as, metamorphism uncomfortable. But the heat is definitely enough to cook the rocks around it. We call that a bake zone. All right, and it's kind of like the bonfire effect. We've referred to that a couple times. All right, the closer you are to the bake zone, the closer you are to the intrusion, the more change you're going to see. And then as you go back from it, obviously there's less heat effect, so you see less and less metamorphism. You can imagine sort of a cross section as you're walking along a edge of a rock face, let's say. You could be walking through limestone, and all of a sudden the limestone starts to look a little weird. And then you're like, oh wow, this doesn't look like limestone anymore. This looks like marble? What is this? And then you see this, big old black pipe cutting up through the middle of it. And on the other side of that pipe, you're going to get marble again. And then it's going to slowly fade back to good old-fashioned limestone. So the bake zones happen in 3D. We experience them in 2D, of course. But yeah, it is a thing, and it's enough of a thing. Again, I have to imagine we first experienced it as they were doing mining or whatever. We're putting roads in for road cuts. As we expose these cross-cut sections, and we actually can see, this stuff happening. Otherwise, it was probably theoretical at first. Somebody theorized that there would be a bake zone around the intrusion. I don't know which came first. We've been mining for a long time, so I'm guessing we stumbled across one and somebody came up with the idea. But you never know. So again, this is for non-foliated only. It's not enough pressure to cause the mineral grains to move around. Just to get thrown in that oven for a little bit. Looks like we got a tiny little area here. Tiny little graphic. What is on here? This is way too much stuff. So all I'd be saying, I don't know why I have this up here even. Let's look at the black one on the right. All we're saying is that around any one of these sills or dikes, you would see some rocks changed. Let's make the brown stuff sandstone and the lighter tan stuff limestone. Okay. So around the intrusion here, you'd see some marbling. Around this intrusion, as we got up into here, you'd see some quartzite forming, and so on and so forth. That's all. But this is way too detailed of a diagram for that. Other than maybe just to remind you, I might have had this in here from when I didn't always get to igneous intrusions, perhaps. Take this as a reminder for what dikes and sills are. In our vaguely horizontal strata, rock layers, okay, sills follow the rock layers, dikes cut through the rock layers. Horizontal and vertical, to use those bad, incorrect words. And yeah, that's it for Metamorphic. Like I said, we don't talk a whole lot about it. I do encourage you to read the chapter, as always. But if you come across stuff in there that I just, glazed over or didn't even acknowledge, please don't fret about it for the test. Metamorphics we keep really, really simple. You need to know about heat and pressure and what each of those do. Okay? And then some random rock names, what one turns into, from the other. Not a whole lot of questions about that. Yeah. Okay. I will swap those out. So it goes into regional, and is there anything else mentioned?
Well, you have a couple of slides that were there that were.
Yeah. This is new metamorphism, at least in my notes. So I will swap that out. But as far as regional goes, I only just talk about regional. Okay. There's not on that one. Is there anything else I skipped? Okay. I'm comfortable with that. Thank you for pointing it out, though. All right, so I will make a concerted effort to swap these out during my office hours. If you guys don't see that happen anytime soon, please send me a reminder, because they are really good things to take notes on, or at least to use as study guides. All right, so let's stop this. Let's stop the recording. Actually, let me save this before I forget. And now stop.